You ever stop and wonder what everything is really made of? I mean, deep down. From the medicine that keeps you healthy to the DNA that literally makes you, well, you, it's all written in a kind of secret code. And that language? It's organic chemistry. So let's crack that code together.
All right, here's our game plan. We're going to cover the chemistry of life itself, meet the hero of our story, carbon, then see how we build with molecules. After that, we'll learn the language of chemistry, figure out how molecules actually react, and then we'll put it all together to see the big picture. Sound good? Let's go. Okay, first up, the chemistry of life. You might be thinking, atoms, bonds, why does this matter to me? Well, the answer is simple, because this stuff isn't just locked away in some textbook. It's everywhere. I mean, seriously, look around. The very code of life, your DNA, that's an organic compound. The proteins that make up your blood, your muscles, your skin, yep, organic compounds. Even the clothes you're wearing, the fuel in our cars, the dyes that give things color, and the medicines that save lives, it's all built from this stuff. This isn't just abstract science, it's the science of you.
So what makes all this possible? It really comes down to one element, the absolute star of the show. Meet carbon, the atom that makes pretty much everything in life possible.
You know, for the longest time, people thought there was something magical about organic stuff. They called it a vital force, this idea that you could only get these compounds from living things. But then in 1828, a guy named Friedrich Weyler was just messing around in his lab and, oops, he accidentally made urea, an organic compound from a totally inorganic one. That one experiment just shattered the whole vital force idea. It proved the chemistry of life wasn't magic, it was just chemistry. The doors were blown wide open.
So what is it about carbon that makes it so special? It really boils down to one simple, incredibly powerful number, 4. You could call this carbon's first superpower.
And this superpower has a name, tetravalence. All that means is that every single carbon atom can form 4 really stable connections, or bonds, with other atoms. The best way to think about it is like a perfect 4-sided Lego brick. It's ready to connect up, down, left, right, any direction. And that is the secret to building all the amazing, complex structures we see in life.
Okay, but it gets even better. Carbon's second superpower is called catenation. So not only can it bond with other elements, it's also incredibly good at bonding with itself. It can link up carbon to carbon to carbon, forming these super long, stable chains and even complex rings. That right there, that's how you go from a single atom to the massive molecules of life.
All right, so carbon is this master builder. But how does that actually work in practice? We know it can form 4 bonds, but it's the way it forms them that gives us this incredible 3D world of molecules. Okay, check this out. This is so cool. The type of bond carbon makes, single, double, or triple, directly controls the final 3D shape of the molecule. So with all single bonds, like in methane, you get this kind of pyramid, a tetrahedral shape. But if you throw in a double bond, the whole thing flattens out. It becomes planar. And with a triple bond, bam! It snaps into a perfectly straight line. The bond type is literally the architect of the molecule.
Now, can you imagine having to draw out every single atom and bond for a huge molecule? It would be a nightmare. So chemists got smart and came up with a shorthand. They started with the complete formula, showing everything, then they condensed it a bit. But the real game changer is the bond line formula. It's just zigzag lines. And in this language, every corner and every end of a line, that's a carbon atom. So much cleaner, so much faster.
But here's a really crucial detail. Not all bonds are created equal. A single bond is like the strong, stable foundation of a house. But those extra bonds you find in double and triple bonds, those are called pi bonds. Think of them as these big, fluffy clouds of electrons floating above and below the atoms. They're way more exposed, and that makes them reactive hotspots. If a chemical reaction is going to kick off, chances are it's starting right there at a pi bond.
Okay, so we've got millions and millions of possible compounds. How on earth does anyone keep track of them all? Well, they developed a universal language for it. And now we're going to crack the code of that language, which goes by the fancy name of IUPAC nomenclature.
And this right here shows you exactly why we need a system. Take formic acid. Its common name comes from the Latin word for ant, formica, because that's where they first found it. Cute story, right? But it tells you nothing about the molecule. The official IUPAC name, though, methanoic acid. That tells a chemist exactly what it is, a 1-carbon acid. The common name is a nickname. The IUPAC name is the blueprint.
I know. A name like 3-ethyl-5-methylheptane looks like a total mess. But trust me, it's just like a set of GPS coordinates for a molecule. You just read it backwards. Heptane tells you the main road is a 7-carbon chain. Methyl is a 1-carbon side street, and the 5 tells you it's at the 5th carbon. Ethyl is a 2-carbon side street at the 3rd carbon. See? It's a perfectly logical system that lets you build the molecule in your head just from the name.
Okay, so we can build them, we can name them, but what do they do? How do they actually react with each other? Well, it all boils down to a really simple game of give and take. And the things being given and taken are electrons.
In this game, you've got two main players. First, you have the giver. This is the nucleophile. The name literally means nucleus seeking because it's rich in electrons, and it's looking for something positive to donate them to, so it can form a new bond.
And of course, if you have a giver, you need a taker. That's the electrophile. It's electron seeking. It's got a spot that's poor in electrons, and it's just waiting for a nucleophile to come along and share.
And really, that's the story of almost every organic reaction. The electron-rich giver, the nucleophile, attacks the electron-poor taker, the electrophile. And chemists have this great little symbol for it, a curved arrow. That arrow shows the entire story. It shows a pair of electrons moving from the giver to the taker to make a brand new bond. It's that simple.
All right, let's zoom out for the big finish. We've talked about the atoms, the shapes, the language, and the reactions. Now let's just take a second to appreciate how these simple, elegant rules can build, well, everything.
So what are the big takeaways here? First, carbon is king. Its ability to form 4 bonds and link up with itself is the foundation for everything. Second, structure is everything. A molecule's 3D shape decides what it can do. Third, there's the logical language, IUPAC, that lets us talk about it all. And finally, all those crazy reactions, they're just a simple story about electrons moving from a giver to a taker. That's really the core of it.
When you think about it, these few simple rules are the basis for everything, from the plastic bottle on your desk to the incredibly complex proteins running your body right now. It really is the ultimate construction kit for the universe. So now that you know the basic rules of the game, what molecule would you build?